Today we'll be looking at chi-square goodness of fit models. A test of goodness of fit for chi-square is a test of whether the distribution of counts in one categorical variable matches the distribution predicted by the model. So we're just going to start with an example. Does your zodiac sign predict how successful you'll be later in life? Fortune magazine collected the zodiac signs of 256 heads of the largest 400 companies. We see some variation in births for each sign, and there are more Pisces, but is it enough to claim that successful people are more likely to be born under some signs more than others? Our assumptions and conditions are very simple. First, we have to make sure the data are in counts and the categories are categorical. Randomization. What test have we done that does not include randomization? It's like a duh. And then expected cell frequency. We should expect to see at least 5 individuals in each cell. Since we want to examine how well the observed data reflect what would be expected, it is natural to look at the differences between the observed and expected counts. Okay, so think of observed minus expected as a residual from last semester. To get an idea of the relative sizes of the differences, we will divide each squared difference by the expected count for that cell. Okay, this is the formula that is posted on your formula packets. This is how we find our test statistic in a chi-square model. So remember, the sigma means the sum. So the sum of all of the observed values minus what's expected squared divided by the expected. It is called a chi-square model, and they are a family of distributions indexed by degrees of freedom, much like a T distribution. When you look up your probabilities, you're going to use table C. The number of degrees for a goodness of fit is n-1, where n is the number of categories. Only for hypothesis tests, chi-square models have no confidence intervals. So back to our example, we have counts of 256 executives in 12 zodiac sign categories. The natural null hypothesis is that birth dates of executives are divided equally among all zodiac signs. The test statistic looks at how closely the observed data match this idealized situation. Are zodiac signs of CEOs distributed uniformly? Well, the first thing we're going to do is our state step, which is here. So our null, our births are uniformly distributed over zodiac signs. All alternate, births are not uniformly distributed over zodiac signs. Okay, so there's our state step. Now notice we have this nice bar chart, and it shows some variation from sign to sign. Pisces is the most frequent. So for our plan step, the name of our test is a chi-square goodness of fit with degrees of freedom. Because there are 12 zodiac signs, we'll do 12 minus 1, which is 11. Now we're ready for our conditions. We know the data are in counts from the 12 signs. The birth dates of executives should be independent of each other, so the randomness is fine. Our expected cell frequency, the null hypothesis, we expect that 1 out of 12 of the 256 births, or approximately 21.333, should occur at each sign, because we want to know if they're uniform. And so these expected counts are all at least 5. For our do step, notice we have our chi-square statistic formula written down. And all we're going to do is, if we look at the first category, we observe 23 people for that first sign. And then we're going to subtract what was expected, the 21.33. We're going to square it, and then we're going to divide by that same 21.33. Then if we look at the second zodiac sign within our table, notice 20 is the second number. And because all of our expected counts are the same, we'll still do 20 minus 21.33 quantity squared divided by the 21.33. And we're going to do this a series of times until we get to that 12th zodiac sign. Okay, this should give us a test statistic of about 5.094. Now, to get our p-value, what I would do is I would turn to that table C. So like I was saying with table C, you're going to go down to 11 degrees of freedom and then pick the test statistic that is closest to 5.904. If you look directly above, like on table B, notice your p-value is approximately 0.926. Okay. If I were to run the test in a calculator, I would choose the chi-square goodness of fit test. I would put into list 1 all of my observed values, into list 2 all the expected values. Degrees of freedom would be 11, and then calculate. Notice we get the same chi-square test statistic, 5.09375, and the same p-value. In our conclude step, we say the p-value is 0.926. The p-value 0.926 says that if zodiac signs of executives were in fact uniformly distributed, an observed chi-square value of 5.09 or higher would occur about 93% of the time. This is not unusual, so we fail to reject the null and conclude that these data show no evidence of non-uniform distribution of zodiac signs among all executives. Let's look at another example. Does the warm, sunny weather in Arizona affect a driver's choice of car color? Cass thinks that Arizona drivers might opt for a lighter color with the hope that it will reflect some of the heat from the sun. To see if the distribution of car colors in Oro Valley near Tucson is different from the distribution of car colors across North America, she selected a random sample of 300 cars in Oro Valley. The table shows the distribution of car colors for Cass's sample in Oro Valley and the distribution of car color in North America. According to www.ppg.com, do these data provide convincing evidence that the distribution of car color in Oro Valley differs from the North American distribution? Okay, so note to self, we have a couple of key indicators. We have random sample of 300 cars. Okay, and we have the distribution of car color in North America. We have provide convincing evidence, distribution of car color differs from North American distribution. Let's remember with our state step, we are going to state the hypothesis we want to test and our significance level. So our HO is the distribution of car color in Oro Valley is the same as the distribution of car color in North America. Our HA, our alternative, the distribution of car color in Oro Valley is not the same as the distribution of car color in North America. Instead of saying not the same, you could also say is different. For our plan step, we're going to identify the appropriate inference method and check the conditions. So for our plan step, we know this is a chi-square goodness of fit model. We only have one category with an alpha of 0.05. We have 300 cars randomly selected. For our expected cells, what we're going to do is we're going to take the total. If we go back to the previous slide and we have the percentages, we take the percentages times the number in the sample, 300, and we get about 69. And we will do the same for the rest of the other categories. So we would take the black observed times the percentage for North America. Okay, and notice that all of our expected counts are at least 5. In our do step, if our conditions are met, we're going to perform our calculations. When we calculate our chi-square test statistic, notice we have 1, 2, 3, we have 1, 2, 3, 4, 5, 6, 7, 8 colors. And so that means our degrees of freedom is 7. And for our chi-square model, notice we're going to take our observed. So the 84 was how many white cars minus what was expected, the 69 quantity squared divided by 69. Plus, if we look at the number of black cars observed, 38 minus expected, 54 quantity squared divided by 54. And we will continue on with this process until we get to the other observed, which was 39, minus the expected for observed, 21 quantity squared divided by 21. And we do get a chi-square value of 29.921. For our p-value, we're going to go to table C and go to 7 degrees of freedom and pick the closest test statistic to ours, and our p-value was less than 0.0005 according to the table. If we're using a calculator, we can do a chi-square CDF and use our test statistic. Notice we have our lower, upper, and degrees of freedom, and our p-value is about 0.0001. Now, remember, you can also run the test in a calculator. So if we look here, we just did run our test in our calculator. We have our chi-square goodness of fit test. Observes are all in list 1, expected in list 2, degrees of freedom 7, and this is what our curve would look like. All chi-square model curves are skewed to the right and shaded to the right. Notice we get the same chi-square test statistic value, and our p-value was 0.000009, and degrees of freedom is 7. And now we're ready for our conclude step. So since our p-value was low, meaning 0.0001 is less than 0.05, we reject the null. We do have sufficient evidence to suggest that the distribution of car color in Oro Valley is not the same as the distribution of car color in North America. We made it to the end, yay!